Hello and welcome to Engineers Mindset Academy. Okay, so in today's class, we are going to begin Cauchy's residue theorem. Now, what is the Cauchy's residue theorem? The theorem can be stated by the formula integral of a function f of z dz is simply equal to 2 pi I multiplied by b1, okay, multiplied by b1, where this b1 is called the residue, okay, where b1 equals the residue. Okay, now what is the formula to calculate the residue itself? To find this residue b1, you simply use the relationship 1 all over n minus 1 factorial the limit as z tends to a of the n minus 1 all over the z n minus 1 multiplied by z minus a to the power of n times f of z. Okay, so this is how you find your residue b1. Now let's identify each of these notations and their meanings. N here stands for the order of z at the denominator. Okay, the order of z at the denominator. This simply means the highest power of z at the denominator after factorizing the denominator. N simply stands for the highest power of z at the denominator. Whenever a question is given to you, the highest power of z at the denominator after factorizing becomes n. And a itself, a from this relationship, a is simply the poles, okay, poles of the denominator. Now we've done this and I said to find the pole of a given function, all you need to do is equate the denominator to 0. It gives you the pole. A here stands for the pole of the denominator. Okay, f of z simply means the given function. F of z itself means the given function. Okay, so this is how you calculate your residue. This is now Cauchy's residue integral, and this is the residue formula itself. The integral is simply what? Integral of a function f of z dz is simply 2 pi I multiplied by b1, where b1 stands for the residue, and this is how you find the residue. Now let's take a very simple example and explain it. Let's say you're given to evaluate the integral, of cos z all over z to the power of 3 times dz. Okay, you're asked to evaluate this integral. Now, this is a very simple analysis to do, okay, using all the ideas I was explained over here. First thing, you know that the integral of this function, f of z times dz, must always be 2 pi I multiplied by b1, okay, multiplied by b1, where b1 is the residue. Now, what then is the function? Comparing these two equations, you have an integral, you have the z here, you have the z here. So this simply means that the function f of z is now what? This part of the equation, which is equal to cos z all over z to the power of 3. Comparing these two equations, we have integral, you have the z, and you have the z. That means f of z is equal to what? Cos z all over z to the power of 3. This becomes your function. Now, the order in this case, order n is equal to, since I cannot factorize the denominator, that means the order remains the power of z. In this case now 3. So n is equal to what? 3. That becomes the order. The next thing to do is simply what? Obtain the poles. To find the pole of a given function, all you need to do is equate the denominator to 0. Therefore, to find pole, which is a, we simply what? Equate denominator. Denominator there is z to the power of 3, equate it to what? 0. If we do this simply implies that z becomes now the cube root of 0. Simply take the cube root of 0 to find the value of z. And we have that the cube root of 0 still remains 0. So this means that the pole, this implies that pole A is equal to what? 0. The pole is simply equal to 0. Now, if you have this, then let's find our residue. B1 is equal to, from the formula we said, 1 over n minus 1 factorial. So you have 1 all over n is the order, in this case 3. So it becomes 3 minus 1 factorial limit as z tends towards the pole. Limit as z tends to A. So z is approaching the pole and the pole A is equal towards 0. So limit as z approaches 0, the n minus 1 from the formula, the n minus 1, where once again n is the order, so this becomes the 3 minus 1 all over the z, also n minus 1, which is 3 minus 1, multiply now by z minus a, remember, z minus a to the power of n, and a is 0, okay, once more, a is 0, so this becomes z minus 0 to the power of n, and what is n? N remains the order, which is 3, multiplied by f of z, and what is our f of z? Cos z all over z to the power of 3, so multiply by cos z all over z to the power of 3. You simply have this. So this becomes our residue. Okay, let's continue over here. Alright, so this simply means that B1 is now equal to, we have here 3 minus 1 is 2. So this becomes 1 all over 2 factorial, the limit as z tends to 0 of the same thing here. 3 minus 1 is 2, 3 minus 1 here is 2. So you have the squared all over the z squared, okay, of the same thing here. You have here z minus 0 remains z, and z to the power of 3 becomes z all cubed, okay, times f of z, which is cos z all over z to the power of 3. You notice now that from here, z to the power of 3 strikes z to the power of 3. That means you have b1 to be equal to 1 all over 2 factorial simply means 2 times 1. The limit as z tends to 0, the squared all over the z squared of, I am now left here with what? Cos z of cos z. So this means that I will differentiate cos z twice. This is the squared over the z squared. So which means I'm going to be differentiating cos z twice. Okay, so b1 is equal to 1 all over 2 times 1 here is 2, limit as z approaches 0. If I carry the first derivative, I'll be left with d all over the z. If I carry the first derivative, I will now be left with z all over the z. And if I differentiate cos, I will simply have minus sine z. You have something like this, minus sine z. Now you repeat the integration again for the second time. Okay, so this is simply equal to 1 all over 2 limit as z approaches 0. If I differentiate minus sine z, keeping the minus as a constant aside, differentiating sine z, I'm going to be having back cos z. So this is actually what? Minus cos z. Now, since this derivative has completely died off, then I can now affirm this limit. Limit as z tends to 0 of this given function, which means wherever you see z in this function, put in the value as what? 0. That will give you the residue. Okay, so let's continue here. Alright, so b1 is now equal to, we have 1 all over 2. So limit as z tends to 0 of cos z. Okay, so we simply have, put down your minus sign, cos, and now z is approaching 0, which means in place of z, you are putting the value as 0. This becomes cos 0. Okay, and this is equal to 1 all over 2 or minus 1 all over 2 because of negative sign. Cos 0 is equal to what? 1. So you have times 1, so which also remains minus 1 all over 2. This implies that the residue B1 is simply equal to minus 1 divided by 2. Now, if you have this to be the residue, then from the integration formula, it is simply integral of f of z dz is equal to 2 pi I multiplied by what? B1. Therefore, the integral of that function f of z dz is equal to 2 pi I times b1. So this is equal to 2 pi I multiplies b1 is minus 1 all over 2. So minus 1 all over 2. So from here, 2 can cancel 2. This simply implies that the integral of the function itself cos z all over z to the power of 3 times z is simply equal to, I am simply left here with minus pi I. And that becomes the answer to that given question. So that is how to apply the residue theorem to solving any integral of a complex variable. Okay, let's pick one more example before we wrap it up on this video. So let's say we are given to evaluate integral around the contour C of the function z all over z squared plus 1, where C is the cycle, z equals 2. Let's say we are given to evaluate this integral. In this case now, we have a cycle, z is equal to 2, which means, I've said this in my previous video, whenever you have something like this is simply called the radius arm. So it means that the radius is what? The radius of this cycle is 2. Whenever you have a variable like this, z in bar equal to 2, it simply means that this is the radius. Usually it appears in this form. Let's say z plus a equals r, where a in this case always stands for the center of the cycle, where you're going to choose to be the center of the cycle, and arrow simply means the radius of the cycle. But now there is no a, which means automatically a here is what? 0. So this simply means that your center is going to be where? At the origin, 0. Okay. Alright, so in this case now, it means what you actually have is z plus 0 to be equal to 2. So the center is going to be what? 0. 2 remains the radius. So the first thing to do is find the poles and then confirm that the poles falls within the cycle before you can solve. Now, to find the poles, remember, you have to equate the denominator towards 0. That's the first thing to do. To find the poles, equate the denominator to 0. Alright, to find pole, okay, which is a, therefore we simply set z squared plus 1 to be equal to 0. Now let's move plus 1 over here. This simply implies that z squared is equal to positive sign, cross an equal to sign becomes negative, so I simply have minus 1. Now to find z, you take the square root of both sides. Therefore, z is equal to square root of minus 1. And we know that the square root of minus 1 is a complex number. So this simply implies that z itself is equal to what? Plus or minus I. Remember, because whenever you're taking the square root, always append positive and negative. So it means that z is equal to plus or minus I. Now, I said in order to get the order, which is n has to be obtained after factorizing what? The denominator. Now, how do we factorize denominator? You have that z is equal to plus or minus I. This simply means that z plus I multiply z minus I will simply give us z squared plus 1. Okay? Will simply give us z squared plus 1, which is the denominator. So upon evaluation, z squared plus 1 is simply what? The poles obtained. It becomes z plus 1 because you have plus or minus I. Since you have plus or minus I, it means that z exists on the positive I and z exists on the negative I. So therefore, you pick one of them, it becomes z plus I. then pick the other one, z minus I. If you multiply these two functions together, you're going to obtain back here the denominator z squared plus 1. You can try to multiply them together, but not forgetting that I multiplied by I is I squared, and I squared is simply what? Minus 1, keeping that in mind. Okay, now if you have this, not forgetting your poles, the poles now, poles A is simply what? Plus I and minus I. These are our poles. Now we have to confirm if these poles fall within this cycle before we can employ the Cauchy's residue formula to solve. Okay, let's try it over there and see. Now, to confirm if a pole falls within the cycle, you simply draw your Cartesian coordinate system. Now, this represents your I. Okay, this represents your I, and down here represents your negative I. So up is positive I, down is negative I. So you can call here plus I, and you can call here plus 2I. Okay, let's take this up a bit, but just to let you know that the vertical pole is always the I direction. So you can also call here minus I, you can call here minus 2I. Now, why are we using minus 2 and plus 2 as the highest range? Is simply because the radius of the cycle is 2. So it must always be up to 2. Now, you want to check if these poles fall within the cycle. Remember, I explained earlier that this cycle can be written as z plus 0 to be equal to 2, which means the center is 0, where we are going to be drawing our radius from. So, on this pole, the center here is always taken as 0. So, remember, you're drawing your radius to be 2. So, which means from here, you count at 2, 1 and 2. This is our radius stops. Also, 1 and 2. This is our radius stops. So, we can now draw the cycle using the given radius. We have something like this as our cycle. Okay, sorry, it's not too accurate, but you have something like this as your cycle. But the poles are what? Plus I and minus I. Notice that plus I and minus I falls within the cycle. Plus I and minus I falls inside of the cycle, which means we are going to be solving the Cauchy's integral using what? Considering both poles. Okay, we are going to be solving the Cauchy's residue formula considering both poles since they fall inside the cycle. So when A is equal to, let's start with the positive. When A is equal to plus I, then you find your residue. B1 is simply equal to 1 all over, remember, 1 all over n minus 1 factorial. What is now n? Let's rewrite this function now, please. Let's rewrite the function. Therefore, the integral becomes integral of the z all over. We have now what? We have simply factorized the denominator, and we obtain that z plus I multiplied z minus I will give us that denominator. So we simply have z plus I multiply z minus I. So this is now, upon factorization, we have our denominator to now be this. After factorizing, now what is the highest power of z after factorization? Notice that the highest power of z here is equal to what? 1. Hence, therefore, order n is simply equal to 1. So upon factorization, that is when you can find the value of what? N. You have to first of all factorize the given function. Okay, so we have n to be equal to 1. Next thing, what is now our function f of z? Comparing this to what? The integral. If I compare this to integral of f of z times the z. Notice that I have the z, I have the z, I have the integral, I have the integral, which means my function f of z from comparing these two is going to now be 1 all over z plus I, okay, multiplied by what? Z minus I. This becomes now my function, okay, and my order n is equal to 1. Now let's find the residue for the first pole. So B1 is equal to 1 all over, remember, n minus 1. What is now n? N is equal to what? 1, the order. So this becomes 1 minus 1 factorial limit as z tends to a, not forgetting, limit as z tends to a, and a in this case is what? The very first pole, which is plus I. So limit as z tends to I, the n minus 1, the n minus 1 all over the z n minus 1. Once again, n is 1, so this becomes the 1 minus 1 all over the z 1 minus 1. Now, the whole of this multiplied by what? Z minus a to the power of n times f of z, which is the function. So, z minus a, you simply have z minus a in this case is plus I, so this becomes z minus I times f of z. What is f of z? 1 all over z plus I into z minus I. So simply multiply by 1 over z plus I multiply z minus I. So you simply have this. Now, notice now that z minus I can actually cancel z minus I. So I have my residue b1 to be equal to 1 all over 1 minus 1 is 0. So I have 0 factorial limit as z tends towards I, the 1 minus 1 is 0. So this becomes d to the power of 0 all over the z to the power of 0 multiplying through by what? This becomes 1 all over. I am now left with what? Z plus I over here. Okay, so b1 is equal to 1 all over 0 factorial remains 1. Okay, limit as z tends to I, remember d to the power of 0 is 1. Anything or any variable to the power of 0 remains 1. So I have z to the power of 0, 1. The z to the power of 0 also 1. So this is now equal to what? 1 all over 1. 1 over 1 is still 1. 1 multiplies everything here remains 1 all over z plus I. Okay? But you have limit as z tends to I. So this simply means wherever you see z in this function, put in the value as what? I. Hence, our residue b1 is equal to 1 over 1 is simply 1. This becomes 1 all over. In place of z here, z becomes I. So I have I plus I, and this is equal to 1 all over. I plus I gives us 2I. Okay, and since you can't keep a complex number as the denominator, you simply multiply top and bottom by I all over I, something like this. Okay, so B1 is now equal to I times 1 gives us I all over 2I times I gives us 2I all squared, but not forgetting that I itself simply means square root of minus 1. That's a complex number. So if I want to find I squared, it means I also have to what? Square the square root of minus 1. So this simply implies that I squared itself is actually what? Minus 1. Okay. So I will simply have this to be equal to I all over, since I squared is minus 1, minus 1 times 2 becomes minus 2. You can simply call this minus I all over 2. So the first residue is minus I all over 2. Let's keep that down somewhere. Okay, we can keep that somewhere around here. So B1 is simply equal to minus I all over 2. You keep this down. So we now solve, consider when A is equal to the second pole. Remember we had two poles. Okay, I've taken it off here. But we had two poles. A is equal to plus I and minus I. So we've considered plus I. Now let's consider minus I. We can still do it over here. Alright, so now consider when A is equal to minus I. So we start from solving our residue. So B1 for the second case now becomes, remember the formula, 1 all over n minus 1 factorial, and n is equal to what? 1. So this is now 1 all over 1 minus 1 factorial limit as z tends to a now is minus I, so it becomes limit as z tends to minus I, the n minus 1, and n is 1, so it becomes the 1 minus 1 all over the z 1 minus 1 multiplied by, you have z minus a to the power of n. So you have a z, okay, minus, but a is minus I, so you have z minus I, okay, times 1 all over, okay, times f of z, and f of z itself is 1 over z plus I times z minus I. So you have z plus I times z minus I. Not forgetting, this is z minus a to the power of n, but n is 1. So even if you put 1 here, it doesn't still change, it remains the same. So b1 is equal to 1 all over 1 minus 1 here is 0. So I have 0 factorial limit as z tends to minus I. Okay, the 1 minus 1 is 0, so I have the 0 all over the z 0 into, mind you, minus times minus is plus. So I have z plus I, okay, multiplied by 1 all over z plus I times z minus I. So you observe now that z plus I cancels z plus I. Therefore, I have b1 to be equal to 1 all over 0 factorial is 1. So this is 1 over 1 limit as z tends to minus I. Okay, d to the power of 0 is 1. The z to the power of 0 is also 1. So 1 times everything here remains. I have now 1 all over. Remember, z plus I is off. So I'm left here now with z minus I. So this is 1 over z minus I. You have this. But you have limit as z tends to minus I. So wherever you see z in this function, put in the value as minus I. Therefore, our residue b1 is now equal to 1 over 1 is 1. Okay, so you simply have 1 all over. In place of this z, you have minus I minus I. So this is equal to 1 all over minus I gives us minus 2I. Once again, we don't allow complex numbers to be at the denominator. So for that reason, you simply multiply top and bottom by I, multiply top and bottom by I. So B1 is equal to, this becomes 1 times I gives us I all over minus 2. I times I gives us I squared. So this is minus 2I all squared. And we know what I squared is. I squared simply means minus 1. So this is equal to I all over minus 2 times minus 1. Minus times minus becomes plus. So it means that B1 here gives us I all over 2. So the second residue, B1 again, is simply what? I divided by 2. Now, to evaluate the integral, we simply say multiply this function by what? 2 pi I. That means the integral of that function, integral of f of z times the z is equal to 2 pi I times b1. But in this case, b1 is 2, so we simply add up the total residue. What is the first residue? Minus I all over 2 plus the second residue, which is what? I all over 2. And if you add these two up together, you have it to be 0. This is now 2 pi I times 0. And the integral of that function is simply what? 0 when you cumulate them. But individually, it becomes 2 pi I. Let's do the individual over here. Okay, individually you have integral of f of z, the z to be equal to 2 pi I multiplied by the first residue, which is minus I over 2. So multiply by minus I all over 2. So 2 cancels 2 here. I times I here becomes I squared. So you have this to be equal to pi or minus pi because of this minus sign here times I all squared. And I squared is minus 1. So this is simply minus pi times minus 1. Hence, the integral of the function f of z, the z is simply equal to what? Pi. So you can call this the first integral, okay? And secondly, when a is equal to, this is when a is equal to, this is when a is equal to plus I. Now when a is equal to minus I, we have the second integral of the function. Integral of f of z times the z is now equal to 2 pi I multiplied by the pole multiplied by the residue, and the residue there is I over 2, so times I all over 2. Once again, 2 cancels 2, I times I is squared, so you have this to be equal to pi I all squared, and I squared is minus 1, is actually pi times minus 1, so the integral of the function f of z dz is equal to minus pi. So individually you have this, but cumulatively you have it to be equal to 0. Alright guys, so that is how to solve Cauchy's residue theorem. Probably in the next video I will come up with 1 or 2 more examples to explain Cauchy's residual theorem. In the meantime, stay safe and cheers of course.